Hello everyone, welcome to our webinar. We'll be talking about live recorder for CI and test environments. So your presenter today will be Bruce Bai. I am Callum, I'm one of the marketing executives at Undo. So I'll just give you a brief introduction about the webinar today and Bruce, as well as a brief introduction on Undo, the company and who we are and what we do. And then I'll hand over to Bruce, who will walk you through the webinar and show you a bit about how you can use live recorder within your test environment. And then at the end, we'll open the floor to some questions. So Undo are a company based out of Cambridge in the UK, and we make a variety of tools for Linux and C++ developers in particular. So we have UndoDB, which is a high-performance reversible debugger. So this helps you step backwards and forwards through your code very quickly to help you solve any problems you might encounter. And then we have Live Recorder, which is our new flagship product, which allows you to capture failures in your production or test environments. Moving on, we're going to talk about Bruce. So Bruce is one of our sales engineers. Bruce has worked for a number of years as a developer. He also has a wide interest in development and test environment. So I'll hand over to Bruce now to walk you through a bit more about this webinar. On to you, Bruce.
Okay, thanks, Kevin. So before we get on to the automated testing side of things, I just wanted to set the scene a little bit. So probably you guys have heard of Maurice Wilks, one of the pioneers of computing. And he had an early realization that a big part of programming was actually debugging the programs. And that remains true today. And he says here that it's a good part of his life was going to be spent finding errors in his own programs. Now, as software projects become more and more complicated, actually, what we find as developers is we spend even more time finding bugs in other people's programs, not just our own code. They're more complex, and debugging has an order of magnitude more complex in turn. So where we come in is allowing you to understand how your software actually came up to a particular behavior. So the situation is where you have some behavior that's not as intended. Think of it as the case where the problem where it can't have happened, but it manifestly has. And so debugging is a process of reverse reasoning to try and work out how that unexpected behavior came to occur. A regular debugger will allow you to pause in your execution and continue and maybe step through or step over functions. UndoDB gives you the facility to actually go backwards in time through your execution. In the automated environments, you can think of it as continuous monitoring of your code. It just gives you that track of recording, if you like, of what's actually happened in your application. And I should note at this point that just like a normal debugger, we don't require any instrumentation when you build your application. You can just touch it like normal, and there's no change to your development environment. So just to show the power of reverse debugging, I want to just show you a very simple example. So this is the entire program for this example. If I just make that a little bit bigger for you. So it's pretty simple. Some of you might have already spotted the bug, but we're going to go ahead and run the application under our debugger. That's that one. So does it? So we've got a sig abort. Let's have a look. Console doesn't tell us very much. Let's see where we are in the stack. So we find that actually we have no stack information here, apart from within the abort. So the stack has been corrupted. So we're now going to step back out of this and find out what's going on. So we just get out of the standard library code that's handling the abort, and we step back one further instruction, and suddenly our stack has been restored. So we've just gone backwards to the point where the stack was sensible, and we can immediately see there's a memset going on here, and it's writing 100 bytes into this buffer B, which has size of only 1 int. So we quickly overran that, we've trashed the stack. With the normal debugger or with the core dump, you just have a snapshot in time, which is after the point of the corruption, and you have no way of knowing what actually led up to that memory being scribbled over. So that was a very simple example that just shows one of the benefits that reversibility gives us. So we'll move on to using Live Recorder in automated testing. We call it the missing piece. So in automated testing, you have a sequence of tests. Some pass, some fail. And the question is, why did the failures occur? In a conventional automated testing environment, you raise bug reports for your developers to take a look at. And what happens all too often is they attempt to reproduce the failure on their development machine, and they can't. There may be something funny about the timing. Maybe with other tests running, it's more likely to occur. Maybe it only occurs on a particular machine because it's configured in a certain way. But that machine is always in use. It's very difficult to set it aside for the developer to try and reproduce the bug on under a debugger or with extra diagnostics. So typically they might add some extra diagnostics and attempt to catch the failure again, and they iterate over and over again. Or it may be that the failure only occurs one time in many thousands of runs. Enter Live Recorder. If you record the failures in your test system, then many of those issues cease to be issues. As long as you capture the failure once in the recording, you can then analyze that using UndoDB. The developer no longer has to reproduce the failure for themselves. So we fix the bugs based on the analysis. Once you understand from the recording why the failure happens, then you can normally construct a reproduction more easily. But it's that level of understanding that live recording gives you. And so those many thousands of tests, many of which would never get fixed because of the difficulty in reproducing and analyzing the failures, are now addressable. So let's go to our Jenkins demo. So we've got we're using the Blue Ocean UI of Jenkins here. We have a couple of repositories. So if I open libUB, for example, and take a look at this build. So we had a pipeline, ran some tests, a couple of tests failed. Those tests that failed will rerun with Live Recorder so that we now have some recordings there. We can actually just run that again quickly. It doesn't take too long. Oops, do that. That's the button. So there we go. So it's rerunning the recording. It's running the tests now on Amazon Web Services. It's predicting that we're going to record these failed tests based on previous runs of the build. And there we go. So the refresh rate is not terribly frequent, so it's got to the point where it's finished, and sure enough, it has rerun the same two failures again. So we can take a look in artifacts. What Live Recorder gives us now is an undo recording as an artifact. So there's one for each of the failed tests. So we can open those up in the browser, or we can download for analysis elsewhere. I'm actually going to switch to the other project, our example project, because that's slightly more illuminating. So we take the race example. Just give it a second while we load up the debugger. So this is loading up UndoDB integrated with Emacs, running under a terminal emulator within the web browser. So in this example, all of the infrastructure is within the testing environment, and we don't need any special software installed, or a developer doesn't need any software installed to do an initial diagnosis. So we can take a look at some of the events, and we see some thread switches. So in this thread switch, we are in sthreadfun. We can step back. Let's do that again. So there we go. We're switching threads because we're doing a mutex lock. It's a fairly common call to do a context switch on. So I should mention that here we're using the same UndoDB engine, as I said, running under Emacs. On the previous example I showed you, we were using our integration with CLine. We also integrate with Eclipse, and in principle, any IDE in which you can use GDB. We act as a drop-in replacement for GDB. So I wanted to show you this example because it's an example where, because it's a multi-threaded application, the timing can be quite specific to the hardware, what that hardware is doing. So having managed to record the failure in this example, this is one where you may not be able to easily reproduce on a developer's PC because of those timing constraints. I'd just like to show you one more example, going back into C-line, where the reverse debugging is particularly handy. Let's just close down the stack smash example. So we need to drop it out of the presentation. So we're on the what we call our cache calculator. So just taking a quick look at the code. This is just test code. It's iterating over this thing called cache calculate over and over again. The idea behind cache calculate is it's a fast method of getting answers to square root, which if we use the math library function every time can take a significant length of time. As the name suggests, we're attempting to cache answers that we think we might be needing in the near future. So having run it, we've got up to just over 2,000 iterations, and we're looking for the square root of 255. The correct value from the math library is 15, but for some reason getting back 0. As I said at the start of the webinar, debugging is a reverse iterative process. The question now is, why did we get 0 from cache calculate? So we can so run back to this line here. We've done that in order to step back into the cache calculate function. And we see here, we're at the top of the function, so the first thing it does is it looks in this cache to see if it's got the answer to 255 already there. And in this case, it finds that yes, it does. So we see that the so number is 255. We should be able to inspect this value. Should print it then. So as we expect, based on the value we got back, the cache answer for 255 is 0. Reverse iterative process. The next question is, how did that incorrect value get put in the cache? In a conventional debugger, what your developer might do is they might add some printfs to try and log what's happening in the cache. That could significantly slow down the reproduction speed. And that slowdown in a more complicated example might actually change the behavior so that we don't reproduce the same issue anymore. They might try setting a breakpoint on cache calculate for number 255 on the grounds that when we were asked 255 is likely to be when we cached the wrong answer. But as we'll see in this case, that's not going to get us there. And it also might, we'd have to check lots of occurrences in which we actually didn't mess up the cache. We saw from the console we've done 2,000 iterations, so you'd expect on average to have actually asked for the square root of 255 8 times already, but it's only on the 9th time or so that we actually got the wrong value. So what we're actually going to do instead is we can set an address watch point on this value. So that's a hardware watch point on the location in the cache that's wrong. So the last time this was changed must be the time at which we put in the wrong value into the cache. So we run backwards, and we find C-line's got some quite nice decoration when you're running in debug mode. It's actually telling us what's going on very quickly. We see that we're putting in square root 2 is minus 2 billion, and number 2 is minus 1. So we're actually trying to put minus 1 and minus 2 billion into our cache. The reason we're doing this is we're being asked for the square root of 0. As I said, if we did a conditional breakpoint on the number being 255, we wouldn't have hit the bug, because I happen to know that in this case it's because of this loop. The implementer of the cache has reasoned that if you're asking for the square root of a particular value, In the near future, you're likely to want the ones either side as well. So it tries to populate the range from -1 to +1 around the one you've requested. But there's no bounds check, so we try to do the square root of -1. And if we look at the structure of the cache line, we find that it's two unsigned chars. So -1 becomes 255, and -2 billion becomes 0 when it's cast down. So that's an example where we have to take multiple backward steps to get to the root cause of the incorrect value. But we've been able to do it very quickly because we haven't had to think about what might have happened and then run forwards again with a new reproduction. Okay, let's go back to the presentation. And we're actually done with the webinar. That's all the content I wanted to show you today. So just hopefully giving you an idea of how powerful reverse debugging can be in terms of capturing a tricky failure, which can then be investigated from the point of failure back to the root cause, rather than having to keep going from a known good point, trying to hit the bad behavior and catch the root cause along the way. Thank you very much.
Cool, thanks, Bruce. We've got one question here actually from Dave. Dave says, do you support multi-thread processes?
Yes, we do support multi-thread processes. So the race example I gave you was a two-thread process. Because we attach in the same way as a regular debugger, we can actually capture everything that's happening in all the threads in a process, and then those can be analyzed in much the same way as you would with a normal debugger.
Cool. Okay, that's actually all the time we have because we said it would be a quick webinar. So thanks everyone for joining us. Hopefully you found this informative. And if you have any questions, feel free to contact us over here at Undo. That's sales@undo.io for any information or any further questions you might have about our products. Hope you found this informative, and yeah, thanks for coming along.